So, what we're going to talk about today is game theory in large payments. And what I want to do, essentially, is I want to give you an example of how important and how useful mathematical and economic models can be in determining and influencing real-life policy. And I'm just going to pick one example from payment systems and large payments, just to demonstrate this single thing, how useful and powerful models can be. So, just to get started a little bit, I'm just gonna tell you what a payment system is. So a payment system is essentially an electronic network over which payments are made from one participant, typically a bank, to another participant. And these networks are used as to just transfer money, basically, across economic actors. So, as you can probably understand and imagine, this is one of the most important elements and most important pieces of the financial infrastructure of any country, right? Payment systems allow us essentially to send and receive money to and from one another. Without payment systems, we wouldn't have any economic activity. So they're one of the most important elements of any country's financial infrastructure. Now, in the United Kingdom, you have several different payment systems that are in operation. Here are some examples of payment systems, and the reason why you have several payment systems is that each system basically is used for a specific purpose. For example, MasterCard and Visa are used to make credit and debit card payments and transactions, and other payment systems are used for different purposes. And PAX, on the upper left corner of this slide, is used to pay people's salaries, for example. And faster payments is used to make bank-to-bank instantaneous transfers. So what we're going to focus on today, the example I'm going to give you today is from this payment system right in the middle. It's the CHAPS. And this is a system that's used to make very large value payments. So let's get a little bit into that. But before that, let me just also say that being a supervisor of the Bank of England, where I'm from, supervises all of these payment systems as part of our financial stability mandate. And oftentimes, we kind of have specific, we may have a say on specific design features of these systems. And to do that, we typically use economic theory and models to understand the dynamics of the system that we supervise, right? So the Bank of England is the supervisor of all these systems. Now, let's zoom in on CHAPS, this large value payment system that I just mentioned. So this is a system that, where where major banks participate and use to make payments to one another, right? And these large payments could be, for example, interbank loans, when one bank borrows from or lends to money another bank, or to facilitate house purchases, right? Anything that involves a very large payment. The important thing about the system is that it's all of the payments are made using reserves. In other words, they're made using central bank money. And for this reason, any payment that's made through that system is irrevocable and final, right? And another important thing is that every payment that's made in CHAPS must settle gross. In other words, if you're a bank and you want to make a payment, you must have central bank money to make that payment, right? So which means that the system is liquidity intensive. And so here's a graphic that's actually, before we get to that, here's a graphic that shows how much money flows through that system on a daily basis. As you can tell, the sums are pretty large, right? On any given day, you have anything between 200 and 400 billion pounds flowing through that system. So we are talking about a large chunk of economic activity. Now, in terms of, as I just said, all payments in that system are made using central bank money. And to make a payment, right, using central bank money, you kind of have two options if you are a bank in that system. You can either use your own available liquidity, and that could be either using, what central bank money you have in your reserve account with the Bank of England,
or you could potentially, pledge some collateral with the Bank of England and receive, and do an intraday repo with the Bank of England, so that, if you want to make a payment, you pledge some bonds with the Bank of England, you get some liquidity for the day, you make your payment, and then when you receive some money back, you kind of pay back the Bank of England and get back your collateral. So you can do either of these things, or if you're a bank, what else you can do is you can you can wait until you receive a payment through CHAPS and then use that payment to make your own payment, right? So it basically, someone pays me and I use that money to pay somebody else. So the basic two sources of liquidity, two sources of funding in CHAPS could be available liquidity on one hand and incoming payments on the other. So the reason why, and precisely because banks, in principle, have to use their own liquidity if no other payments are coming in that they can recycle. This is why the system is kind of liquidity intensive, right? You must have you must have substantial reserve balances with the central bank to be able to make these payments. Okay, so let me just now zoom in on an example, just to set the stage and just kind of show you what kind of problems and dynamics arise in this type of system. Suppose you've got two banks, right? Barclays and Lloyds, and they each need to make a payment of £1 billion to one another. And this payment has to be made today. But of course, there's no other explicit obligation as to when exactly during the day this payment needs to be made. Both of these banks just know that they need to make a payment of £1 billion to one another today. So here's how things now start to become interesting in this setup. These banks are going to have to use some kind of reserves, right, to make these payments. But the important thing is that, at least one of these banks must have $1 billion in their reserve accounts to make these payments. And the reason for that is what we just discussed earlier, is that in principle, if you are the first bank to receive the 1 billion, right? Then you can take this 1 billion and send it back to the bank that just paid you and make your own payment that way. So if at least one of the two banks has 1 billion available, then both of these payments, a total of 2 billion, can be made. So that's kind of interesting. And the reason why it's interesting is because it creates all kinds of incentive problems. So if in principle a bank can make a payment and others can use that payment over and over and over again to make their own payments, then essentially the bank that made the payment is kind of providing a public good to this network. It's kind of providing a service to this system, because it's committing some of its own liquidity, which is costly, and it enables other banks to make payments while the other banks don't have to use any of their own liquidity. So that's what we in economics we call a free rider problem, right? Every bank in the system has an incentive, right, to delay their own payments. Why is that? Because that way they can wait until someone else makes a payment first. So once they've received someone else's payments, they can use these payments, right, and make their own payments without committing any of their own liquidity. The problem with that is that if everybody's waiting until someone else makes the first move, right, the system can fall into a gridlock. Or, payments are going to be delayed for the day, and then the system could become very vulnerable to any operational outages. Right. So this is a situation, by the way, that people who do game theory call volunteers dilemma, and you can clearly tell why it's called the volunteers dilemma. And interestingly, it's a situation that basically arises in many occasionally, very frequently, on many occasions in life. So let me just double check that everything's okay so far. Okay, so far so good. So let me give you an example, my favorite example from a volunteer's dilemma that basically characterizes what's going on here. So this is a beautiful church in Venice, Italy, Santa Maria Gloriosa dei Frati. So here's what's nice about this church. If you go inside this church, there's a painting in one of the corners of the church. There's a nice painting, but it's in a dark corner, so you can't really see it very well. So the other thing is now there's this vending machine right in front of that painting, right? So this machine, you can drop a coin if you want, and then what's going to happen is, a light is going to turn on, it's going to illuminate the painting, and everybody can see the painting. Now imagine a group of people, standing in front of that painting, right? They're gathered around it, and someone now has to drop a €2 coin to illuminate the painting. The question is, who's going to do it? Right? Imagine all these people, right? Everybody wants to see the painting, but everybody thinks, that someone else maybe should drop this €2 coin so that the painting is illuminated and then everybody can get to see it. Well, that's precisely what the problem is in chaps. In this very liquidity intensive system, everybody wants someone else to make a payment to load the system with liquidity so everybody else can go on and make their own payments. So let me just spend like 3 minutes and add a little bit of formalism just for the sake of it, because this is in fact a mathematical conference. Let me give you a very extremely simple setup. I like extremely simple. So suppose there are n players, right, in this volunteer's dilemma game. Each player can volunteer or defect. If someone volunteers, if at least one of the players volunteers, then everybody gets a positive payoff, right? And whoever volunteers is just going to have to incur this cost C. It's like, think of this cost C as the €2 coin that you have to drop into that vending machine to light the painting. And in this very simple setup, those of you who are kind of familiar with game theory, it's very easy to kind of see that there are, pure strategy, Nash equilibria. In fact, there are n of them, as many as there are players. And in each of these equilibria, at least one person volunteers. Now, there's a problem with these Nash equilibria. The problem is it's not clear who's going to volunteer, right? In practice, we have here in a situation where, although you do have some equilibria, it's not clear how to get to this equilibria, because everybody might be waiting for someone else to volunteer, right? And in the end, it's highly likely that the whole thing becomes trapped. Everybody gets trapped and nobody volunteers, right? And the solution in these types of situations is that you must have some kind of coordination or impose some kind of social norm that's going to be required to determine who should volunteer, right? So this is what's happening in this pure strategy Nash equilibria. Now, if you look at in this setup, if you look at mixed strategy symmetric equilibria, you kind of things get a little bit more interesting. So suppose, for example, I get that. Okay, 5 minutes, yes. So suppose, for example, that, every person volunteers with a probability P, and I'm not going to go through the details. What's going to happen in the end is that at least you end up, if you kind of solve this very simple problem, you end up with a situation where in equilibrium, you have someone volunteering with a positive probability, and that's the last expression in this slide. But the interesting thing is that as n, which is the number of players, grows, the probability that at least one of them volunteers goes down. So we're essentially back into the same problem, right? We need coordination. So the model, basically this simple intuition, the volunteer's dilemma and game theory tells you that to solve this kind of free riding problem that often arises, you need some kind of coordinated effort. So now the regulator comes in, the Bank of England comes in with all its statutory powers and legal powers, and basically is going to play the role of this coordinator. So what the Bank of England says now is that we're going to impose these throughput requirements. In other words, we're going to tell banks that you must, and we're going to tell you to do that, on average, every day, make 50% of your daily payments by noon and 75% of your daily payments by 2:30. Now, if you haven't received any money by that time, then you must commit your own liquidity to meet this goal. In other words, we mandate that there's some degree of coordination in the system. And the interesting thing is that this actually has pretty remarkable results. So this chart shows you the percentage of payments that are being funded either by recycled payments or intraday repos from the Bank of England or own liquidity or own central bank reserves. And what you see is that you see this purple line at the top, which shows you that more than 85% of the value of payments that go through this very large value payment system are actually being recycled, precisely because you have this regulator who comes in and mandates and tells people to coordinate so as to resolve the failure that would result otherwise. So essentially, it's like going into this church and telling every person who's standing in front of the painting to contribute a few pennies. If everybody does that, then you kind of quickly get this €2, and then you basically get to illuminate the painting, which, by the way, is Titian's assumption, right? It's a beautiful painting. So what's the morale of the story? And I'm going to pretty much be done now. So even the simplest models, right, can have incredibly powerful policy implications, right? Don't discount something that's simple. And it's essential for us and for you guys who are studying, any of you who are students in this program, to kind of really, have a good grasp of the models that you are studying, and also be able to identify any real life situations and problems where these models can actually be applied. That's going to be really important. In my opinion, what's often the case is that people who are very good at maths and models, they tend to ignore some of the applications that are out there and are craving for some modeling. And on the other hand, you have people who are busy with policy issues who to a large extent may ignore some of the mathematical tools that are available to them or might be available to them to solve this problem. So it's important for all of us to be able to somehow try and bridge this gap between actual policy and mathematical modeling. And with that, I'm going to be done. Thank you very much. Σας ευχαριστώ πάρα πολύ. Αν έχετε ερωτήσεις, στείλτε τες μου μέσω email και θα χαρώ πολύ να σας απαντήσω.